We are now going to prove this theorem that we are now going to prove the theorem that for every NFA n, there exists a DFA m whose language is the same. And first, we're going to consider a construction without the epsilon transitions for simplicity. And given an NFA n, we're going to construct a DFA m, which has a different set of states, the same alphabet symbol, and some transition functions delta prime, start state q prime, and set of accept states f prime. Okay, so q prime will be, unsurprisingly, the power set of q. So it will have a lot more states than n. The start state will be just the set containing q, where q is the start state in n. F prime would be the set of the set of states in M, which remember are subsets of states of n, such that S contains some element from the accept states in n. Okay, and the transition function delta prime will follow the transition in every state in the set. So delta prime SA, remember S is a set of states of n. Okay, so the value of delta prime will be the union over little s in big S, so every small state in n, okay, of delta SA. Okay, and a different way to write that it would be the set of t's such that the t is in delta SA for some s in S. And this belong h should be an equal sign. Okay, because delta just outputs a state. It remains to deal with epsilon transitions before we do examples. Okay, so let's define for a set S of states, E of S is the set of states Q that can be reached from some state little s in big S traveling along either none, 0, or more epsilon transitions, possibly many. We think of following the epsilon transitions at the beginning, as soon as you start the computation, or right after reading an input symbol in sigma. This is just a convention that makes it easier to follow the definitions. Okay, so here is the theorem again, and here is the construction which now includes the epsilon transitions. Okay, and it's just like before. Q prime is the power set of Q. Q prime, now the start state Q prime is the E of the set containing the start state of N. Okay, E is also called the epsilon closure. F prime is like before, and delta prime is also like before, except that we always take the epsilon closure E of the sets that we consider. Okay, lots of symbols. Let's see an example. Okay, here is an example of an NFA to a DFA conversion. So on the left we have an NFA, and on the right we're going to build an equivalent DFA. On the left we have 3 states. So on the right, our DFA will have a set of states which is the power set of the states on the left. So we're going to have 8 states, and each state is a subset of states. Okay. the start state of the DFA is the epsilon closure of the set Q NFA. Okay, the start state in the NFA. The start state is 1, and the epsilon closure would be 1, 3. So here is our start state. Okay, the set of accept states are the states that contain an element of the set of accept states in the NFA. The NFA only has one accept state, 1. So now every state on the right which contains 1 will be accept. We have 4 accept states. Okay, and now we have to put the transitions. So in the DFA, the transition from state 1 to A, reading symbol A, would be the epsilon closure of delta NFA 1A, which is the epsilon closure of the empty set, which is the empty set. Okay. So you can think of the empty state as a sinc state here. Let's do another one. What if you read a B? Okay, it would be the epsilon closure of 1B, okay, which is the epsilon closure of 2, which is just 2. Okay, let's now look from state 2. If you read an A, you have the epsilon closure of delta NFA to A. This delta NFA to A will be the set 2, 3, okay, because the NFA from state 2, if you read an A, you can go back to 2, and you can also go to 2, 3. And so you have this error here. So what happens if you read a B from state 2? Think about it. What do you get? If you read a B, you will get, by similar reasoning, the set 3. Okay, we can continue in this way. If you're in state 3 and read an A, you will go to the set 1, 3. What happens if you read a B? You will go to the empty set. Okay, let's now do something a little more complicated. Let's say now you're in state 2, 3, okay, and you read an A. Okay, so then remember, we're going to apply delta NFA to each state in this set. So we apply to this 2 here and to this 3 here. For each of them, we are going to compute the delta NFA. So the first one gives us the set 2, 3. The second one, the set 1. We take the union, and then we take the epsilon closure, E of that, resulting in a set 1 to 3. What happens if you read the B from 2, 3? Think about it. This is where learning happens. Okay, if you try something now, pause the video, do that, and then see if you got it right. If you read a B, then you would do delta NFA to B, union delta NFA 3B. That's the set 3, union empty set. Epsilon closure of that is still the set containing 3. Okay, from 1, 3, reading an A, you would cycle back to 1, 3. What happens if you read a B? If you read a B, you will take delta NFA 1B, delta NFA 3B. Okay, that's the set containing 2, union empty set. Epsilon closure of that is still just 2. Okay. From 1, 2, reading an A, you will go to 2, 3. Similar reasoning. Reading a B, you will go to 2, 3 again. Okay, so we can put both labels here on the same arrow. Okay, let's now do something more complicated. Let's say we have the set 1 to 3. Okay, delta DFA 1, 2, 3 reading NA would be the union, it's the epsilon closure of the union of three things, delta NFA 1A, 2A, and 3A. Okay, and this gives us the set 1, 2, 3. What happens if you read a B? Okay, if you read a B, you will get, by similar reasoning, the set 2, 3. The empty set is left, well, and there is no state in the empty set, so the transitions are just cycling back to itself. That's it. That's an example of a conversion. Okay, we can delete the unreachable states, right? You don't have to show them by our convention, and you will get a simpler DFA. So in this case, you can remove this and think of it as a sync state. Okay, let's do another example of an NFA to DFA conversion, and another three-state NFA that's written on the left. Again, the set of states in the DFA is a power set. Okay, the start state is the epsilon closure of 1, which is just 1. I'm going to say 1 for the set containing 1, okay, for simplicity. The accept states are those that contain 1, like before. And let's start to put some transitions. So if you read an A from 1, you go to the empty set. What happens if you read a B? So if you read a B, then something interesting happens with the epsilon transitions. Okay, let's see it slowly. You would do epsilon transition of delta NFA 1B. Delta NFA of 1B is 2, 3. Okay, 2, 3, but the epsilon transition, remember, of 2, 3 would be 1, 2, 3. Okay, because if I'm in 3, I can also reach 1 by reading an epsilon. Remember, the epsilon closure E, right, is the set that you can get to by reading 0, possibly 0, so it includes the starting set, or any number of epsilon transitions. Okay, let's do another one. From state 2 with A, you will get to the state 1, 3. From state 2 with B, you will get to the empty set. From state 3 with A, you will get to the empty set. From state 3 with B, you will get what? You will get also the empty set. From 1, 2 with A, you would take the union of delta NFA 1A and delta NFA 2A. That's empty set union 3. Epsilon closure of that gives you 1, 3. And if you read a B, you will get to set 1, 2, 3. From 1, 3 with A, you will go to the empty set. From 1, 3 with a B, you will go to 1, 2, 3. From 2, 3 with A, you go to 1, 3. And from 2, 3 with B, you will go to the empty set. Finally, 1, 2, 3 with A, you take the epsilon closure of these 3 delta NFAs, which is empty set, 3, empty set, and you just get the set 1, 3. And if you do a B, you will cycle back to itself. From the empty set, again, you cycle back to itself. Again, we can delete the unreachable states, and if you think about that, there's actually many unreachable states here. Like this state here, the state 1, 2 cannot be reached. Okay, there is no arrow that points into 1, 2, so you can remove it just like a sync state, and you would just get a DFA with 4 states. Summary is that NFA and DFA recognize the same languages. Now we can return to the question of closure under various operations.